Well, as if this unit on kinetics, how fast a chemical reaction goes, wasn't confusing enough or potentially confusing enough with all the mathematics to describe how fast a reaction goes. The kinetics, chemical kinetics. Let's throw in here at the end some conceptual ideas that are equally as tricky sometimes. Most reactions happen because of a collision of a couple of particles. The warmer they are, the faster they move, the faster they collide, the faster the reaction usually. And these reactions may actually happen in more than one step. It may take two or three steps, two or three little collisions and transfers and breaking of one bond, forming of another. These individual steps or parts to the story are called um, elementary steps. Now, uh, the reaction mechanism is a story about how these one or two or three individual elementary steps can combine to give the overall end product we see. The story is called the reaction mechanism. Here's a reaction I think we'll come back to toward the end, where ozone in two steps breaks down to give O2. But it doesn't just happen really quickly, for one thing. It takes some time. One of these two steps ends up being slower. And whichever step ends up being slower is actually the step that controls the rate of the reaction overall. Like if I were just to look at this data, not data. If I were to look at these two, there's one chemical equation here, another chemical equation here. There's one elementary step here, another elementary step here. If we add those two together, as we've been known to do in sort of a Hess's law kind of a thing, we get this overall reaction. In the past, we've looked at the heats involved, but now we're just going to look at intermediates and or catalysts and or the slow step. It turns out the slow step always determines the overall rate law. And so far as we've told you to this point, you must look at some data based on concentrations, amounts, or initial rates to be able to even guess at the rate law. Imagine a highway construction or some kind of slowing down in the traffic, as often happens on the interstate or even on smaller roads where the lanes are restricted and the cars have to slow down. It causes a huge backup on the interstate. But what we're trying to say is this also happens, or we imagine this happening, in chemistry as well, in an elementary step. So I drew a picture down here. It says here the rate law of the rate determining step determines the rate law of the overall reaction. So we could imagine particles want to go from here over to here, and we're flowing from left to right. There's two steps. There's one step here and one step here. In my first picture, I've drawn the first step being very fast, probably some sort of equilibrium where the particles could flow left to right or right to left. And they would do so especially if they're blocked up here. And step 2 is the slow step. Step 2 being the slow step for whatever reason. Maybe it's orientation to molecules, maybe it's just not that likely to happen. But it jams things up and only a few particles get through this step per second, say. On the other hand, we could have it the other way around. We could have the first step being slow and the second step being fast. Or imagine 3 steps, throw in another barrier there. Or you can imagine, I've never actually traveled out east much, driven on the roads. This happens in Europe as well, where you have a toll road. And maybe this toll booth is open, but this one's closed where everybody has to slow down and pay their money to get to drive on the highway. I can imagine, sort of. It happens. Anyways, it's a slow step, either this step in this story or this step in this story, that determines the overall rate law for the reaction. more terminology. Unimolecular means one molecule involved in a step. Bimolecular means two molecules involved in a step, and usually these molecules are colliding with each other. Termolecular means three particles, which is actually increasingly rare because with three particles involved in an elementary step, I'd have to have three particles colliding with each other at the same time in the same place at the right orientation with the correct energy. And by the time that happens, the reaction goes very, very slowly. Many times there's just one particle or two particles involved in a collision or in an elementary step. So here's an overall reaction where I have hydrogen peroxide decomposed. The iodide ion serves as a catalyst and helps that H2O2 break down into water and O2 gas. I think that's a balanced equation, good for us. We want to propose a mechanism. Say, I wonder how that happens. Well, here's one idea. Some harebrained chemist sitting in a dark, dingy office thought this up one day. I'm kidding. Sort of. Maybe. I don't know. Could be. They said, well, what if the H2O2 collides with an iodide ion? The iodide ion bonds with one of the oxygens, stripping it away from the H2O2, leaving water. And I have some kind of IO minus ion. But then that IO minus, there's a minus there, ion collides with another H2O2, creating H2O again, and an O2. So what would that look like? I'm trying to think about how this H2O2 could come apart. It looks like this IO minus ion donates its oxygen to another of these oxygens to make the O2 over here, leaving one of these oxygens on the hydrogen. Boy, I would like a nice animation of this. In any case, this is the first elementary step. This is the second elementary step. Perhaps we're just hypothesizing this, or perhaps we have experimental evidence to support this. In any case, this I negative iodide cancels from the left and the right. If your species, in this case I minus, is present in the beginning and the end, it's called a catalyst. If your species, in this case IO minus, is present in the middle as a product in one step and a reactant in the next step, this one cancels this one, or even in a later step, it could be, I could imagine, that's called an intermediate. The overall reaction is just H2O2, two H2O2s reacts to give two H2Os and an O2. Experimental, who typed this up? Not me, I didn't, I promise. Experimental rate law. So I would have to have had found this from somewhere else, some other data. So if I'm told that this is the rate law, then I must somehow say that one of these steps yields this observed rate law. And indeed it is true that the slow step here determines this rate law. But you don't know how yet, because we've warned you, we've cautioned you not to do this. So this seems silly. In the beginning of the chapter we said don't do this, and now we're going to say do this. If it is an elementary step, then I can say that the reactants in the elementary step contribute 1-to-1 to the rate law. So one H2O2 particle, molecule, one iodide ion, and that's to the first power, and that's to the first power. But if you do this for an overall reaction like this, it's a huge mistake. And we'll say that again and again. I think I've said it again and again. I'll keep saying it again and again. If and only if a reaction is an elementary step where one particle collides with another, then for that rate law, for that step, it depends only on the concentrations of the reactants that are molecules, species that are colliding with each other. And this indeed seems to contradict what we told you earlier in the chapter. But we were looking at overall reactions. So when we're looking at elementary steps and mechanisms, 1A as a reactant results in this rate law. 2A's as reactants results in this rate law. 2A's and a B reacting, colliding, very rare, would happen pretty slowly. 2A's and 1B. But again, this is a huge mistake to do this for an overall reaction. Interesting. Now these would have to be slow steps, like maybe this was a slow step in a mechanism. Maybe this was a slow step in a mechanism. You can only do this for elementary steps, not the overall rate law. Again, molecularity, 1, 2, 3, unimolecular, bimolecular, termolecular, very rare. Saw that terminology earlier. There's an ozone reacts with NO. The experimental rate law, so they found this out from somewhere else, is 1O3 and 1NO. It seems like it's O3, 1 and NO1, but this may happen in several steps. And so it's been proposed or observed that, first of all, an O3 collides with an NO. In a sense, giving 2 oxygens to the NO to make it NO3. That's odd. An oxygen atom, single oxygen atom, which is rare, exists for a nanosecond, a picosecond, fraction of a second, as an intermediate. Looks like the NO3 here also is an intermediate here. And they collide again with each other to transfer back one of the oxygens from the NO3 to the oxygen atom. So we could say maybe we just made this up, or maybe indeed it's observed that this is what happens. In any case, you add this one to this one, the slow step to the fast step, and we say, does this elementary step as a slow step, does it agree with what was observed through some other data? And evidently 103, 103, 1NO, 1NO. So this was what was observed, matches what we're theorizing or predicting happens in a slow step collision. So either they have to give you the rate law as observed from other data and say, tell me something about what the slow step is. In this case, they wouldn't tell you this is the slow step. Or they could tell you the slow step and say, predict what the rate law would be if this really is the slow step in this mechanism. This is one we saw earlier? No, yes, whatever. Oh, this one is inconsistent. So indeed, this added to this cancels the oxygen atom, and O3 plus NO yields NO2 and O2, which is the same thing we had up here, but this this mechanism, using this as a slow step, does not agree with what's observed. This would predict just 1O3 to the first power, and instead I see an O3 to the first power and NO to the first power. So that's not going to fly. That's not going to fly. What do you know? These are really weird ideas. I'm waving my hands in the air as I'm talking to you, trying to get you to believe this, but it just takes a whole bunch of practice with questions like this. So it tells us something about the slow step, or it might tell us something about the slow step and an equilibrium that might have come right before it. Here's an example of, maybe. Overall reaction, proposed mechanism, NO2 collides with F2, creates a fluorine atom intermediate that collides with another NO2 to give into a NO2F. If I really wanted to get some gumdrops and toothpicks and think about how these might collide and break old bonds and form new bonds, it wouldn't be a bad idea. But if the observed rate law from other data is this, can you tell which of these two is the slow step? Would it be the first one is the slow step, NO2 to the first, F2 to the first? I think it would be. Because if I had this as a slow step, I'd have a fluorine atom as a reactant, and so somehow that would have to occur in the rate law, but there's a problem with that. You can't really have an intermediate as, you can't have an intermediate appearing in your rate law, or you really shouldn't, because it's hard to measure, because there is no intermediate in the beginning to measure the concentration of. Here's a possible mechanism, slow and fast. What's the overall reaction and the rate law predicted by this mechanism? Well, let's see, if I add those two things together, I think the chlorine cancels, and that's about all it cancels. This chlorine atom cancels. I have two NO2Cls react to give two NO2s and a Cl2. The slow step would be the one I always focus on, and I'd say my rate equals some constant K times this thing, NO2Cl to the first power. Yeah, that's just what I said. How about this one? No, fun, more. So in this one, I'm told the slow step, so I focus on the slow step. I think the rate law would be something like O3 to the first power, NO2 to the first power. NO3 cancels, this is an intermediate here and here. Okay, yeah. Interesting. Remember, the other possibility is that they would tell you the rate law and the proposed mechanism and say, they could say, is this mechanism consistent with the rate law? Is there a slow step that would allow this observed rate law to agree or be in effect? There's another problem too, though. If I have an intermediate as part of a slow step, or excuse me, Lord, got a frog in my throat. If we have an intermediate as a part of as a reactant in the slow step, I got to get rid of it. For example, look at this one. Here's my overall. If I add these two elementary steps together, I should get this. The two I's cancel here and two I's cancel here as intermediates. But if this is the slow step, my iodine atoms aren't really as reactants or products, especially reactants in my overall reaction. So how can I measure them? I can't. They are there, generated only for a fraction of a second. So, but what I am allowed to do is take if those iodine atoms came from a fast equilibrium in a preceding step, or the step exactly preceding, I'm allowed to substitute in for those what it was that generated those in the first place. So I'm going to take that I2, instead of writing this, two iodine atoms, I'm going to write I2 instead of that. I'm going to write that in place of this, and then I2 will just be the first power. Substitute, I wrote it out in more detail here, so substitute. So if this is not in the overall rate law, in the overall reaction, I need to substitute in and see what I get. It's hard to believe that you can do this mathematically or chemically, like what are you saying? But what we're really just saying is you can't measure the concentration of an intermediate, and where's that intermediate coming from? It's dependent on the fast equilibrium here, which as a reactant has the I2. So I just, in essence, substitute in I2. These constants here, who cares? We don't care what they are. Sometimes you can measure them, sometimes you can't easily measure them, but they all combine to give just one constant that we've been talking about this whole chat unit. So they just kind of lump all together, and we find the value of that probably experimentally. Yeah. Here's another one. If you care to look at it, if you care to fall asleep or turn the video off, who would really blame you? My goodness. This one's more. This one has a one elementary step and two elementary steps. In that, I guess it's saying we have a couple of transition states. So NO2 collides with another NO2 to make an NO3 and an NO. The NO3 then collides with another CO to give CO2 and NO2. Looks like the NO3 cancels as an intermediate. They told us here this is slow, so if this is slow, I have NO2 and another NO2, so that's two NO2s, describing the rate of this elementary step. And does that agree with what is observed? Lo and behold, it does. I wouldn't want to have this as a slow step. If it was a slow step, I could include this in my rate law, but I couldn't really include the carbon monoxide as oh no, I could. Fiddlesticks. Oh, I could include the carbon monoxide, but I couldn't include the NO3 as it doesn't appear in the overall reaction. It's an intermediate. So I'd have to take that and substitute in for where it came from, but that would be further complicated because it's got an NO here, and oh my goodness. Do I really want to go there? I don't really want to go there. But it would work that way. So we've been saying this already. The elementary steps must sum together to be consistent with the overall equation, and they must also be consistent. The slow step must be consistent with observed data that we observe from some different set of experiment. Boy, here's a super complicated looking one. Fast step, slow step. I focus on the slow step. If I'm told the slow step, my eyes go there right away. Look at the O3 and the oxygen atom. Except the problem with that is we don't have an oxygen atom in our overall, whoever typed this up didn't do a very good job. I don't have an oxygen atom in my overall chemistry, my overall reaction. So I probably would have to substitute in for that where it came from. The oxygen atom was generated here, and that's got to be shifted over there, and it's just kind of a mess. Ugh. We've only talked about zero order, first order, and second order. But the truth of the matter is there can be inhibitors or fractional orders, which gets confusing. Not for us in this class. Here's one more. If I told you this, could you tell me what the overall chemistry was here? And also what the rate law was? And if you'd like to look at the last slide on the PDF, go for it. I'm not going to show it to you now. I'll be mean. Thanks for watching, guys, and we'll see you in class.